I wanted to start off by just talking a little bit about VLEO generally, the environment itself, because that has such a big effect on what we can achieve with satellites operating in that regime, and indeed define VLEO because I think as Discoverer, or certainly as the University of Manchester, we're trying to use a consistent definition of VLEO, but occasionally we hear different definitions and we say, no, the Manchester one is correct. So we'll try and stick with that pattern. So first of all, some details of VLEO itself, the atmospheric environment. So what we've got here is a plot of altitude on the left against the density of the atmosphere. Okay, and what we know that varies with solar activity. So at higher solar activity, you get more absorption of UV in the upper atmosphere, and that raises the density effectively. So which is why we see this variation in the density. Also just put on there the Kármán line. So this is the edge of space as generally agreed upon in Europe, okay, down at 100 kilometers, where in theory, operating something low than this altitude, you can generate enough lift so it becomes an aircraft. So we're above this line, okay. What I've added on there now as well is the kind of the typical delta V requirement you would have for a satellite operating at these different altitudes. So we've got another x-axis along the top here. And you can say this is a typical satellite. I think I said 2 tons, a couple of square meters cross section. And what you see over a typical lifetime of say 5 years, I think in this case, and what you see is that as you get lower in altitude, the amount of delta V you need to compensate for drag over the lifetime of the satellite increases. At 600 kilometers, it's maybe a meter per second. You could probably ignore that to a certain extent. When you get down to 500, it becomes 10. At 400, it's about 100. At 300 kilometers, it's a kilometer a second now that you need. So the drag is having a significant effect on the design of the satellite. And that's how we define VLEO in this sense. We've said this is the drag threshold at about 450 kilometers. Above that, you can get away just about by ignoring drag. Below that, you absolutely have to take it into account. You have to compensate for it in some way. And so it's this band that we call VLEO that we'll talk about in a minute. We've also got some examples of different satellites on here. So some Earth observation satellites, some of the ones you'll have been hearing about. So MVSat was, obviously it's not functional now, but up at 800 kilometers, Rapid Eye at 600, WorldView at about, probably one at about 500 kilometers. You get below this drag threshold, you don't see many Earth observation satellites at all, apart from the ones coming off the International Space Station, which is at 400. Goche, a kind of Earth observation satellite in many ways, down at 260, 270 kilometers, is the exception, and to a certain extent some of the inspiration for what we think we can achieve with VLEO satellites. And so it's this band that we're calling very low Earth orbit, okay, where you can't build a satellite in a traditional manner and expect to have long lifetimes for Earth observation. The other factor associated with this is the atmospheric composition, which is kind of critical here. So what we've got on the right is a kind of normalized atmospheric composition distribution. So obviously the density is increasing rapidly as we come down, but if we look at the percentage of different atmospheric species at different altitudes, then you can see, okay, down at ground level here at 0, then it's that normal expected mix of molecular nitrogen and oxygen, fine. In the range we're talking about in VLEO, the majority of this atmosphere is atomic oxygen because of that extreme UV breakdown of the upper atmosphere. So what we're then designing is aerodynamics to work in a flow of atomic oxygen at 8 kilometers a second, okay, which it sounds fairly challenging, and indeed it is, okay. So that's the environment. What this presentation is about, though, is trying to look at that, the concepts themselves and the benefits and the challenges associated with these concepts. Preferably kind of angling in this direction to show that there are more benefits than challenges, which we think there are, which is why we're doing Discoverer in the first place. So in terms of the benefits, there are significant payload benefits. There are also some issues, which I think Santiago you've already identified. There are launch benefits, and there are environmental benefits as well in terms of the space debris environment. On the challenges side, there is the atmospheric drag and the atmospheric interactions with the satellite. And indeed, that again, I noticed you didn't mention it, but the short line of sight, which is to do with the communications link as well. So I'm going to focus largely on these benefits and to a certain extent in the challenges, and kind of ignore this because we know that other people are working on higher bandwidth communications to get data down. That trend is only going to carry on, and VLEO satellites will benefit from that trend in higher and higher bandwidth communication systems for satellites. So focusing first on payload benefits. There are many, okay. What I've got is just a top-level boxes here, which will then dig down a little bit to look at the detail of them. In terms of optical payloads, we can get improved diffraction limited resolution. Okay, this is the key benefit we've already identified. You also get improved radiometric performance, effectively, because you're closer to the thing which is reflecting that diffuse energy that you're then collecting. The same is true for synthetic aperture payloads as well. You get an improved signal return, and we'll have a kind of a quick look at the fundamentals behind that. And there are generic benefits as well, such as improved spatial improved spatial positioning, effectively, which will allow you to locate that data onto the ground. And very carefully written, improved angular field of regard, which helps a little bit, but not as much as you might think. So we'll kind of work down through these different factors. First of all, I feel like I need to do just a kind of very top-level, basic Earth observation 101, because that kind of ties in with some of the definitions as well. So angular resolution we've got at the top there. This is the ground resolution, and it's related to these different factors here. H being the altitude of the satellite in a very simple terms, lambda being the wavelength, and delta and the d there being the diameter or the aperture of the optics, effectively. We've also got some definitions here. So the field of regard, which is this wider angle, is what you're happy for your camera effectively to look at to obtain your Earth observation imagery as you're passing over the ground. The optics themselves have a much narrower field of view. So what you're actually taking the image of is some smaller fraction of this field of regard, which you're then focusing on, which isn't necessarily directly below the satellite, is typically off to one side or the other, after all. Now, because the Earth isn't flat, although some people think so, because the Earth isn't flat, we have another issue here, in that this image that we're getting, which is a nice array of pixels from our sensor, when it comes to actually what you're actually seeing on the ground, it's not this nice distribution of equally sized areas on the ground. In fact, it's my rather bad attempt at trying to show the distortion that you get. So the pixels towards the edge of this field of regard are going to be distorted because of the curvature of the Earth, effectively. Actually, as you get lower, the Earth appears flatter. So actually that helps us a little bit, which is where that field of reduced angular field of regard comes in, or increased rather. So yes, the best resolution is limited by this Rayleigh criterion, the diffraction limited resolution. And once we start digging down a little bit more, I've now changed, instead of just the altitude, I've got this slant range, which is typically because you're not looking down at the nadir, straight down at your target. And we can show some general, therefore, relationships because of these parameters. Clearly, if you reduce the slant range here, then your angular resolution increases. Right? This is the key benefit that we see in all the different systems. But one of the factors here is limiting this alpha, which is the angle with which you're viewing the Earth from, is also important. As you look further and further towards the limit of the Earth, you're seeing more and more distorted imagery. Buildings get in the way of features behind them. Local terrain does as well. So there's typically a limit on how far off the vertical you want to look at the ground, which effectively therefore limits this angular field of regard to whatever that acceptable angle might be. Now, if we look at the radius of the field of regard, which therefore is what you can see from your satellite at any one point in time, then obviously we've got a bit of simple trigonometry here. But the radius of that field of regard is tied into the different angles within that triangle. So again, they're all linked together depending on how far off the nadir you want to look and what that acceptable off-vertical angle is. Now, as with all systems modeling, and that's effectively what we're doing here, we're trying to look at the whole design space. Typically what you're doing is you're varying one parameter and seeing what happens to all the rest. And they tend to be the extreme cases, therefore. So this is one extreme case whereby we are just taking the same optics on a system and seeing, okay, what happens as we get closer and closer to the ground. So there's several lines on here. The important ones in the first instance are the blue and the red lines. What we're looking at here is the radius of that field of regard as it varies with altitude, okay? And what we see is, looking first of all, that's the red line on this radius of field of regard. As you get lower, that radius obviously shrinks, okay, because you're becoming close to the target, which is what you were mentioning. Okay. What we see though actually is that variation, because the Earth is getting flatter. If you compare that to some kind of linear variation, it's actually slightly better than that, but you know, not hugely, slightly better than that. In that the angular field of regard we got on the left here, so that's that angle that we had before. It's basically increasing as you get lower, from maybe 31 degrees through to about 35 degrees in this particular example. So there's a small improvement associated with it. Now you could say therefore that, okay, we're reducing the field of regard, that's becoming a bit of a problem. But you can also take the other extreme point of view, okay? In this one I've said, well, okay, let's leave the optics alone. We've got the same resolution, same aperture. Okay, so we're not reducing the size of our payload as we reduce the altitude of our satellites. What does that do to the resolution within the field of regard? So this is the off-nadir viewing angle, again with varying altitude as we go down. And if we take an example of, say, these contours are therefore showing the ground resolution as we move off the nadir through to a 60 degrees off angle. If we take the example of, say, a 1.5 meter resolution here, which we've got here, so it's 600 kilometers, 1.5 meter resolution. That gives us an angular field of regard of about 200 kilometers. As you get lower, because your resolution is increasing, you can look further off axis, right? And in fact, at 300 kilometers, that angular field of regard is bigger. So it depends on which parameters you fix in this. The key change here is that viewing angle has now gone up to 46 degrees, which is, okay, perhaps you will have to tell me what's acceptable in terms of that kind of off vertical viewing angle. But what that kind of shows is the answers we're probably looking for are not at the extremes. They're probably somewhere in the middle of these different parameters. Some reduction in the size of the telescope, but maybe not shrinking it directly proportional to the change in the altitude, for example, to give us what the customer wants, effectively in this case, and to try and figure out what those parameters are. So yes, and that's basically the summary of what I've just tried to say. So it's those extreme cases. We can either maintain the ground resolution by reducing the aperture, but then we get this reduction in the field of regard. Or if you maintain the optical aperture, you can increase the field of regard, but you increase the off vertical viewing angle. The optimum is probably neither of these, but something in between the two. On the other side, if we're looking at the signal-to-noise ratio, which is of course related to the radiometric performance effectively. Okay, so when we're thinking about signal-to-noise, normally we consider the noise. In everything I've done in this presentation, I've ignored the noise because I'm assuming it's staying roughly the same, right? Because it's normally majority to do with the sensors and the optics, which they don't particularly change with the altitude. But what we see is two key factors here. If you think about the light that's being reflected back off a surface, it's distributing as 1 over the distance squared. And also, the other side of this is the collection area of your telescope, of course, affects the signal to noise as well. So if you make the telescope aperture bigger, then again, the signal to noise increases with the diameter squared. So again, if you just look at those two extreme cases, one of which is if you consider reducing the payload aperture as you get lower, so you maintain the same resolution, then effectively these two things cancel out. And you get no change in the signal to noise as your telescope gets smaller and lower. Okay, that's one extreme. So all things equal, that's great. The other option is if you maintain the optical aperture, so the other extreme, then in fact you then get a signal to noise increase with 1 over r squared, which means it means that you can change the way you're doing that imaging, smaller, what's the phrase I'm after here? Having shorter imaging packages. I'm trying. Exposures? Exposures, thank you. So shorter exposures, and therefore that actually gives you other benefits in terms of the MTF and things like that associated with the imagery. Moving on to synthetic aperture payloads, it's a very grainy figure. It's not my figure, so I'm not going to use that excuse. It's a very grainy figure. I'm going to focus only on this particular, the very simple mode, the strip map mode that you get as a satellite moves across the ground, and it's imaging as it goes along. Okay. Now, A little bit, again, a little 101 about synthetic aperture radar, because again, you kind of need to do that to put things in context. And synthetic aperture radar is horribly counterintuitive, I find, as well, which really doesn't help in this way. So the key principle here is that you've got a radar antenna. It's transmitting a pulse of radio energy. You're doing it kind of off the nadir deliberately, because what you want to happen is for that pulse to reach the ground. You're then getting the return from the nearer part here back up to the satellite. And at later time, the part from the further part of that area. So you get a pulse and then a distributed return, which is telling you about different parts of this cross-section that you're getting, okay? And as the satellite moves along, you're synthesizing a larger aperture as well, which gives you the part which is horribly counterintuitive. Because what you actually find then, if you look at resolution of a synthetic aperture radar, you get some equations which have absolutely nothing to do with the altitude, okay? In fact, nothing to do with the majority of factors going into the design. You find that the resolution in the aperture, so the azimuth direction, which is the long track passage of the satellite, is proportional to half the length of the antenna. Right? No matter how high you fly, how low you fly, it's half the length of the antenna, which, let's say, counterintuitive. In terms of range resolution, it's all to do with the pulse duration. Okay, so the shorter the pulse duration, then the shorter the return, effectively. So, which is to do with how long it's taking to interact with the surface and come back to the satellite. Okay, which again has nothing to do with the altitude of the satellite. So you have to separate these different terms. So at first glance, flying lower in terms of resolution has no benefits whatsoever. Okay, but the subtlety here for VLEO satellites is in all the other parameters which go into the design of the system. So if we were to look at one of the key parameters here, which is this pulse repetition frequency, or PRF, right? So what that means is that there are limits on what pulse repetition frequency you can have, and to avoid ambiguities in the imagery that you're getting. One of them is effectively a minimum pulse repetition frequency to avoid azimuth ambiguity. So this is again, the azimuth is the along track direction. And what that means is that the pulse repetition frequency has to be greater than the velocity of your satellite divided by the length of the antenna. Sorry, the ground resolution, effectively. Because if you're moving along, then otherwise you're blurring out your pixels by the fact that you're moving along. Similarly, there's a maximum pulse repetition frequency in that you have to wait for one pulse to reach the ground and for your signal to come back from the nearer part of the piece of ground that you're imaging, and wait for it also to come back from the furthest part before you're transmitting the next pulse. Otherwise, you're getting multiple pulses from different parts of that ground track at the same time, and you're losing the information that you're actually after. So you get a pulse repetition frequency that has to be less than this term here, which is due to the geometry in that triangle, where this is the range at the far side compared to the range at the near side over the speed of light there, which is also related to the swath widths, which I won't go into. But basically, we could, if you substitute all these terms in here, you get a minimum pulse repetition frequency, which is proportional to the other dimension of your antenna. Okay, so you now got pulse repetition frequency is linked to the size of the antenna, and you can rearrange that to look at the minimum antenna size that you need, related to those D terms here and here, as a ratio of pulse repetition frequencies, which we know from practice as that range from 1 to 2. And these other terms here, this loose change at the end that defines the size of your antenna. What we end up then with is that this area of the antenna is proportional to the altitude, which is, okay, this is now a useful relationship that we can actually use for systems modeling. In other words, if we halve the altitude, we can halve the area of the antenna. Halving the area is quarter the mass. Okay, so half the mass. So there are now significant benefits in terms of the SAR payload itself. Another factor with this is actually the signal to noise, or effectively the power received back from the energy transmitted to the ground and then received back at the antenna. Now, the equations for synthetic aperture radar are even more horrible. So what I've done is looked at the simple radar equation in this example to try and illustrate what's actually going on there. So if we have a power source, PS, that's generating that pulse, and we're looking at what power is reflected back from the target on the ground, then obviously there's the gain from the antenna focusing that energy towards the area you're looking at. There's a radar cross-section in terms of the scattering back from that target. And it's dropping off at 4 pi r squared because it's, again, being distributed into the space. This is the free space loss. Similarly, when we look at the power received back at the antenna, you get similar effects in there. There's the gain of the antenna again. That's that PR term that we had before. And again, you've got that 4 pi distribution coming back off the ground down to the satellite. And it's worth bearing in mind that that power received is again proportional to the signal-to-noise ratio of that system, effectively. I've thrown in here an equation that characterizes that gain in terms of wavelength and the antenna area, again, which means you can put all these together and look at, okay, the power of the source, so how much energy you need to transmit to get a certain energy of return, and you get this relationship which has both the range to the target, to the power of 4 in this case, but also the area of the antenna. Remembering that, of course, we just looked at from before, the minimum area of the antenna is proportional to the altitude, means that the power that you need to transmit is proportional to the range squared. Okay, so again, halving the altitude of the SAR system means you only need a quarter of the transmitting power, which, you know, that's a significant change in any payload requirement, right? So this is where we see there are some significant benefits for SAR payloads, far apart from the fact that, hey, it's a nice aerodynamic shape as well. It's a minimum drag shape which helps us. So SAR perhaps looks more promising in some ways than optical stuff. In terms of geospatial resolution, the position accuracy of an image, which is how well we can locate that image onto the ground exactly. So you mentioned, you know, things like, where is that tank exactly? This is to do with a number of different factors, one of which is the optical alignment, which is typically taken out in calibration once the system's been launched. It's to do with the positional accuracy, which again we don't have any control over, but that doesn't change with altitude. It's to do with the GPS on board and things of that nature. What we do have is control of the satellite attitude here. So how accurately the satellite is pointing directly affects where we think the image is located onto the ground. Okay, and that in terms of that transition to a position on the ground, again it's that attitude error times the range to the target. So again, if we halve the altitude, we halve this error in that geospatial accuracy. Okay, so again, there's a direct connection there between the change in the altitude and benefits for the payload, which I've kind of vaguely tried to summarize in this rather poor figure. So we looked at the payload benefits. There are lots in there, but it is a design space that we need to explore by putting in all the relevant requirements and trying to see, okay, what are the optimum outputs we can get here. In terms of launch benefits, it's much harder to characterize in that if we wanted to optimize launch vehicle trajectories for VLEO, we'd need to be a launch vehicle company, right? So what I've done is trying to find launch vehicles that actually have published this data in a usable sense. Not all have. A lot of them say, please apply for more information. But there are some which have published that data in a helpful manner. So first of all, Falcon 9, unfortunately, it does go down to 200 kilometers, so okay, that's interesting. And what we see is this general trend that you're gaining about 200 kilograms per 100 kilometer altitude reduction compared to a 600 kilometer altitude launch. Okay, so this is bearing in mind that the 600 kilometers altitude, it's 7.8 tons. 200 kilos. It's a smaller addition that you're getting there, but it's a beneficial one, certainly. Soyuz is another one, much more modest in this case in terms of what the data they've actually provided. If we look at some smaller launch vehicles, though, Vega's quite interesting. So you're getting a 50 kilogram increase per 100 kilometers reduction in altitude. So, perhaps in some cases there's an extra satellite in your system. Hard to say at this point, but it's a percentage that's quite high. The other one, of course, is a very small launch vehicle, which I'm not suggesting it's a good choice of VLEO, which is it's Pegasus, which provides a lot more information, but of course it launches only very small payloads anyway in the first place. But again, what we're seeing here, as we per 100 kilometer increase, is a 9.4% increase in the launch payload up mass effectively. So this is starting to become very significant. So all the launch vehicles that we look at, that benefit is there. You can get more mass up effectively as you get the altitude lower, which reduces the cost of getting your satellites onto orbit if you're maximizing and actually using all that mass on the launch vehicle. In terms of environmental benefits, this relates largely to space debris and the space debris environment. So I'm sure many of you will have seen this figure. This kind of shows you the trend in space debris over time, which is effectively a NASA plot that I've got somewhere else because they've got some nice annotation here. And what we see is a lot of the debris that we currently track in low Earth orbit is a product of fragmentation events. Okay, it's from collisions on orbit, it's from upper stages coming apart, exploding. But with some very significant aspects in there which made big changes to the space debris environment. A really important one here is this Cosmos-Iridium collision, which produced several thousand bits of trackable debris from the collision of two satellites on orbit. Okay, this is the thing we definitely want to avoid. It's not only those direct collisions, but all the fragments, the smaller fragments that aren't being tracked. If they hit your satellite, they can destroy it. So we are very aware that you want to be in an environment where that space debris risk, that collision risk of the smaller debris, is avoided as much as possible. Looking at this in a different way in terms of the range varying with orbital altitude in very low Earth orbits, again, this larger change is to do with both the Cosmos-Iridium collision, but also the Chinese anti-satellite test, which produced, again, an awful lot of debris. And so you see this change. In this case, this is in spatial density. So this is a way to try and assess how much debris is producing a risk to your satellite in a particular orbital altitude. So the higher this number, the greater the problem, effectively. And what we see as a result, largely of those two incidents, this huge change in the spatial density and therefore the collision risk, which is directly proportional to that on satellites. The interesting bit then I want you to look at is what happens in the VLEO range, even when all these horrible things are happening at higher altitudes. So if we look at the 450 down to 100 kilometer range here, it's all very small. So we like this, okay? This is very significantly reduced collision risk compared to kind of more traditional orbit altitudes for remote sensing satellites. And it's not only the population now, but if we look at, okay, this is an older study now by ESA, which looks at the projected space environment going forwards. This is based on the kind of business as usual case, so we don't particularly worry about space debris propagation or try and clean things up. And what you see, therefore, is that this massive increase in the amount of space debris, that spatial density. But again, if you look at the VLEO range, which unfortunately disappears behind this peak at the far end, but you can see because the atmospheric drag that we're trying to overcome here is actually cleaning the orbits for us, keeping that spatial density down, and therefore making the collision risk much, much lower. So this is fantastic for another good reason to fly satellites at this particular altitude. Not only that, but if we then consider our satellites, our VLEO satellites at the end of their lives, if we then look at, I was trying to find a good figure which showed very low Earth orbit, deorbit times as a general thing, which is quite hard to find. But basically we're looking at typically, certainly for the CubeSat we're launching as part of the DISCOVERER program, is kind of on this line here. And we're looking at lifetimes at the very most of a few years down to tiny fractions of years. So if you have VLEO satellites, they reach the end of their operational lives, they're going to come down very quickly, which again, no debris pollution problems from that. So these are the environmental benefits, effectively. They're really helpful for us. Moving on to the atmospheric drag and interactions and atmospheric interactions side of things. So I've shown you this figure, again, put it back into your mind. This is the environment we're operating in, largely atomic oxygen, and increasing density as we get to lower altitudes. First of all, it's worth talking about atomic oxygen erosion. Some of you will be aware that European new atomic oxygen erosion facility. This is one of the first outputs that they've published from that, and actually shows a piece of Kapton that was originally up to the level of this little peak here. This is a peak of a little bit of metallic contamination. which is shielding the kapton underneath it, but all the rest of it's been eroded away significantly, which is what typically you see in the low Earth orbit environment. So what that means is certain materials are a definite no-no for satellites in low Earth orbit because they get eroded away. We're not interested in using those eroding materials. We're interested in the ones which are resistant to atomic oxygen erosion, largely. Okay, like certain metals, for example. And the key strategy here that we're trying to achieve, we're looking at VLEO satellites, is first of all, if you imagine this big circle is the drag that's acting on the satellite, what we want to do first of all is minimize the drag using the aerodynamics. We can't eliminate it entirely. That's it's not going to happen. So you get perhaps a reduced amount of drag on the satellite, which we're then compensating with electric propulsion. Now, by reducing the aerodynamics, we're obviously making the requirements for the electric propulsion much easier, which is therefore a key aim of this kind of two-pronged approach to addressing atmospheric drag and therefore the shorter lifetimes again that you're mentioning as you get lower. So drag, again, back to 101, no surprises here. It's the standard drag equation which applies as much to satellites in low Earth orbit as it does to aircraft. Okay, but the terms in here though are much more complicated when you actually start looking at the detail. So the density, okay, we know it's a function of altitude, but it's also a function of solar activity and geomagnetic activity. So that makes, this bit slightly harder to quantify. Apart from that as well, we know there's this problem with, if we're looking at atmospheric models, the density, Alco, you'll probably tell us more about that as well. The density, from certain measurements, if you're using satellites to look at the density or trying to model the density, then there's this causal link between what CD values you're using and therefore what density estimates you're getting. And from the steering committee last year, even some of the discussions with UCL, there was some of the ground-based measurements just aren't lining up with on-orbit satellite-based measurements by a factor of 2, I think. And that's what we're saying. So there are some kind of issues there in terms of what's really going on in terms of that density. The velocity itself, it's not just the orbital velocity of the satellite, which of course is a function of altitude too, but also the atmosphere is rotating with the Earth, okay, which therefore gives you some changes in the angle to the flow, to the flow compared to that velocity vector of the orbit, which varies therefore with latitude, and there's also thermospheric winds on top of that, which can act as disturbances and changes to the drag. In addition, then we've got the CDA on the end, which you can call a specific ballistic coefficient perhaps, which is dependent on the geometry and also on the gas surface interaction, so how the individual molecules are interacting with the surface of the satellite. And this is where our aerodynamic materials come in and what we're trying to develop in that particular area. But to do that, I need to talk about gas surface interactions a little bit. And what I've tried to do is try and simplify the theory behind those gas surface interactions to try and indicate what we're actually after in this way. So what we see on, or what we think we're seeing on most surfaces on satellites in very low Earth orbits is diffuse thermal re-emission, so a complete accommodation of that surface. What that means is that we've got a molecule in the flow coming into the surface, it's interacting with the surface, it's exchanging all its energy, and it's being re-emitted in a kind of diffuse fashion at the thermal energy of the surface, so much, much slower. If we consider what that means actually in terms of the drag or lift force here, is that the majority of that is to do with the direct energy exchange with the surface. The re-emission produces, if we've got a very steep angle like we've got with this surface here, a very slight amount of lift in that sense, but lift is, in this case is about 1% of drag, so this figure is massively exaggerated. And so regardless therefore of that geometry of the satellite, putting a pointy nose cone on the front makes no difference to the drag on the satellite. Okay? Or very little difference to the drag on the satellite. And so if this is true, then it's all about the cross-section of the satellite that you need to minimize in order to minimize drag. You have no other controls but to limit this factor here, which is that cross-sectional area. Which is why Goche was the shape it was, to try and minimize that cross-section, right? What we're after is to try and identify materials which have either quasi-specular or specular reflections of that atmospheric gas. So if we look at, say, a quasi-specular re-emission here, instead what we're seeing is that, again, the molecule's coming in, it's interacting with the surface, but we're getting a skewed distribution at an angle of specular reflection from that surface. if we can achieve that, then what we're seeing then is more lift and less drag, effectively. And so pointing nose cone on your satellite then starts to reduce the drag on the satellite. Okay, so this is what we're trying to identify. Drag is reduced. You'll note, though, there's an important caveat here. You need to get the angle of the surface above 45 degrees compared to the flow. Otherwise, in fact, you increase the drag on the satellite. So you need pointy geometries and back to streamlining and 1960s stuff. Better still if we can get to fully specular emission, so that we're scattering those molecules off the surface without actually changing the velocity of them. Then again, you reduce drag even further, and as a side effect, you're generating lift, but you can counteract that by different surfaces on the satellite to remove it. So this, if we can find materials which do this, then okay, we're in our golden land, and we'll forever change the world. Okay, so what we're after then is trying to identify materials which produce those kind of specular reflections. Of course, the space environment at the moment that is closely linked to those gas surface interactions. So what this figure is trying to show a little bit is linking those different types of reflections with the environment at increasing altitude. So what we see is that we go to higher altitude, we see different gas species in there, as opposed to molecular atomic oxygen. And what we see in terms of the changes in the drag on the satellites is we see more specular reflections. So we know it's possible. The question is, as you get lower and you get more atomic oxygen and you see this more diffusory emission and more absorption to the surface, so there's that chemical process with atomic oxygen, which is the key factor that we're all very well aware of, which is why we're designing a tunnel to produce atomic oxygen and look at those gas surface interactions with materials, to try and find those which actually will still give us more specular reflections, regardless of the fact that we're dealing with atomic oxygen. It's fairly well, we're fairly well aware that generally there are material dependencies on gas surface interactions. Okay. We know that surface roughness has an effect, which is why we're looking at, in the first instance, at 2D materials. So we're working with the group in the University of Manchester that pioneered works in graphene and things of that nature, but also other 2D materials to see what properties they have in terms of reflecting atomic oxygen. We also know there's links to the molecular composition and the lattice configurations. Surface cleanliness is another example, but also flow velocity and incidence angles. So we know we need to look at what the flow looks like at different incidence angles of those materials to the flow. The other half of this is the drag compensation. I'm not going to talk about this to the University of Stuttgart, because you know more about it than I do. I've chosen one of your nice figures. But the other part of it is the drag compensation, clearly, where we're looking not just at wonderful atmosphere breathing electric propulsion, which I think is highly promising and certainly lets us fly lower and for longer than a traditional EP system would do. But also we're looking at more general EP systems, electric propulsion systems, because at certain altitude ranges they're almost certainly more mass beneficial to the concept than a full atmosphere breathing propulsion system would be. Another side of this is to do with, so we've talked about the benefits, we've talked about some of the challenges here. Another challenge is to do with just the control of the satellites. Okay, so as soon as the aerodynamics become significant, then you have a control problem, which has many and varied implications, therefore. And what I've got here is we're considering in this particular slide aerodynamic attitude control as an augmentation to traditional attitude control systems. Okay, so there's an expectation here, certainly from our part, that remote sensing satellites will almost certainly have to have traditional wheeled systems in there for that fine pointing. We don't think that we'll be able to do fine pointing just with the aerodynamics, partly because the response times are very low at certain altitudes, because the forces are relatively small, but also because of the high variability in the atmosphere itself. Okay, so two concepts here, one of which is having an aerostable platform like GOCE, which of course is good for things like synthetic aperture radar. With some caveats though. One of the caveats there is atmospheric co-rotation. So as your satellite travels around the Earth, because the atmosphere is appearing to coming from different directions, even apart from the thermospheric winds, that means your satellite's going to want to point itself off the velocity vector, which is actually need to maintain it on for that synthetic aperture or radar measurement. Which kind of leads us to this question about whether or not we therefore need to add things like aerodynamic surfaces to keep aerodynamic trim, to keep the satellite stable to the orbital velocity direction and not to the atmospheric flow direction, for example. Air stability is also really good in case of a safe mode. So if you have a single event upset on your satellite, you lose all the control, the onboard computer reboots, you don't want your satellite spinning out of control. Okay, so air stability is good as a backup as well. Having said that, on the other side of it, the neutral stability has its benefits too. So if you have an optical payload, so a traditional optical remote sensing satellite, the telescope is fixed in the satellite and you're pointing the whole satellite at the thing you're trying to image. If you've got air stability and you're trying to do that, you're now fighting the aerodynamics to be able to point it in any other direction than the neutral, the stable position. Whereas if you have a neutrally stable satellite, like a fighter jet, you can point it in any particular attitude and it will stay pointing in that direction, which is great, except for you lose all those benefits over there. But it does make it insensitive to those atmospheric variations and the atmospheric co-rotation. So, okay, interesting. One of the challenges here, though, is almost certainly as soon as you do that, you're now presenting a greater drag cross-section to the flow. Okay, swings and roundabouts. Also, if you are having drag compensation in there, which direction is your thruster now pointing in? Okay, it's not necessarily pointing against the drag on the satellite. It could be pointing in some other attitude because you've repointed the whole platform. So it raises some different questions about whether we separate the payload from the platform pointing. So if you look at, for example, a manned air vehicle taking remote sensing data, that payload where it's pointing, it doesn't care about which way the aircraft's pointing in the flow. But then you've got a huge extra control problem in terms of moving optics on board your platform. But maybe that's the direction we should look at. And again, it's a question I'll talk to you about another time, because we think we can probably get it from some of the GOCHE data, is do the small scale variations in the atmospheric density cause structural vibrations that we need to then worry about when it comes to the MTF for optical measurements, for example? I think that's to do with, therefore, the fine resolution and the density of the atmosphere itself. So, and that applies to any aerostable concept we look at. If we looked at this idea, though, of active aerodynamic control on its own, can we achieve that? I think there are some interesting issues that we perhaps need to address. It's possible, but we know there are variations in the density, and the thermospheric winds mean that if you do have aerodynamic surfaces, then the amount of torque that you get from that aerodynamic surface is varying depending on the atmospheric conditions. So you either need some really clever predictive control system, which is trying to guess what's going to be coming up, or you end up with an atmospheric sensor, like you have to put the INMS, so you're measuring that flow onto the satellite and the density in real time to know what control actuation you're actually going to get from the system. So again, extra complexity, but maybe that's possible. The actuation force is certainly at the higher end of the VLEO range, is only comparable to solar radiation pressure. So these aren't significant forces, which makes it very difficult, therefore, to control the satellite in any quick fashion, which is why we suspect the combination with more traditional actuation methods is better. And it's worth pointing out as well, if without any specular reflections from those materials, you can only actuate in pitch and yaw. Effectively, if I deploy a panel and I get drag, then I turn one way, but I can't control my roll at all because that relies on lift. Okay, so aerodynamic control becomes limited unless we find those wonder materials that we're trying to identify. And finally, in terms of aerodynamic orbit control, because there are some opportunities in here, constellation deployment's a key one. Nick will tell you all about that, so I was in PhD, about basically using differential drag, you can control the orbital plane of the satellite. Basically, if you launch all your satellites into a single orbital plane, if you increase the drag on one of them before the others, it will start to lose altitude. You then get differential changes in the plane of the orbit because of the J2, Earth ablatant effects. And so you can now just start distributing those satellites into different planes. So that becomes one possibility. With the specular reflective surfaces, though, you can also generate lift, of course, which, okay, that can therefore help you change the orbit perhaps even more quickly by using some of those, using it to help steer the satellite into different orbital planes. And we've already theoretically proved that you can target re-entry by modulating drag, okay, which is perhaps more helpful for things like drag sails. But if you've got a large Earth observation satellite and you're worried about bits of it surviving re-entry, if you can modulate the drag on the way down, you can deliberately target a specific point in the ocean, which therefore is really helpful. And that's targeting both latitude and longitude, because if you give it sufficient time in advance. So this is perhaps something we'll see on larger VLEO platforms as a possibility. So in conclusion, we've got lots of benefits, a deliberately shorter list of challenges. But of course, this is where most of Discoverer sits, right? It's addressing these challenges and looking at how we can tie all this together to pull out these opportunities, okay, of which there are many. And I think I'm going to stop. Okay?